Programmable logic controllers, programming functions. In this presentation, we're going to be looking at external I/O, internal bits, latching and unlatching, timers, and counters. All of that, or the lower four, I guess, are going to be inside the PLC program. Only the external I/O would be the one where we would have physical items that are being wired up to the PLC cards. Well, let's start with external inputs and outputs. This is where external devices are connected to the PLC I/O cards. This is used when signals are received from or sent out to external field devices. So in this one we have 2 push buttons and 1 light. Internal inputs and outputs are software only. There's no external device connected. Therefore, the creation of logic for inputs and outputs which are integral to equipment, so things like latching and unlatching coils, timers, counters, soft keys on equipment, touchscreen inputs, and graphic inputs. None of these things leave the PLC. They're not external devices, and so they're all interior to the PLC program. Internal bits are confusing because they're shaped the same as standard inputs and outputs. So the shape that you see is the same as what would normally be used as external I/O. This is because they offer the same functionality, going true, false, or on or off in a program. The main difference is internal bit inputs are controlled by instructions within the program, not a field device applying voltage to a terminal. Internal bit outputs do not energize a field device with voltage. They are used almost as an internal relay to trigger further control within the program. The address given to the symbol is what identifies it as an internal bit. And finally, while the number of actual inputs and outputs for a PLC program is determined by the hardware, the number of unique internal bits can be in the hundreds or thousands. So let's take a look at a basic example of an internal input and output with no external devices connected. And this is going to be for soft touch keys, which are the F1 through 4 here on the front, and graphics in behind. Now what you'll notice is that the address given for these two symbols is different from the standard I or input and O for output. We have a K and we have a B. This unique address or letter is determined by the manufacturer. So you'd look it up in the manual and it would say, oh, for internal bits, you're going to label it B1 or address it B1 and go from there. So K1 is for F1 push button, and B1 we're going to say is going to initiate a little light to illuminate on the screen. So when someone comes and presses F1, it will then act as a standard input, but it's all internal. And so it's going to go true, and that will allow a light to illuminate on the screen. Now, internal inputs and outputs can also be used as duplication of existing logic in a program. So that's another way that we can use it. So duplication of other existing logic would be things like this. We have 2 separate push buttons and 2 separate lights, input 1 and input 2. Now you can see output 1 right here is also duplicated here. Output 1 is being used as an internal bit and an input at that. So by using the same address, this is going to go true whenever that is on. So this is kind of acting like an internal relay. Interesting application. The internal bit in this program is addressed the same as the standard output. In doing this, the internal bit will go true each time output 1 goes on. So there we go, input 1, output 1 goes on, output 1 internal bit goes true, and now I'm going to push in input 2, that's going to go true, and output 2 should come on. Now if I release my finger from input 1, output 1 should go off, and output 1 should go off, and now we don't have a continuous line of true logic and output 2 goes off, right? This is in the middle. Think of it as a series connection. You need to have a continuous, uninterrupted line of true logic in order for an output to go on. If we take a look at internal bits for latching and unlatching and timers and counters, it's going to be doing the same type of thing. It's something that is an application that uses internal bits for additional control. These are the most common applications. So let's start with a latch and an unlatch coil. Internal latching and unlatching instructions, again, these are software functions, and they're also referred to as set and reset instructions. Operation is the same as a latching type relay, where you need to energize to close and energize to open. So I'm just going to go through a brief example of a mechanical latching relay just so we remember how that operation functions. So there are two separate coils, a source for each component here, and there's a light that is going to be turned on, and a push button here for unlatch, and a push button here for latch. When I press down this push button, current flows through, and it moves the contact closed, and that turns on the light. And when I release the push button, it remains in place because it's a mechanical latching relay. If I want to turn the light off, I then have to press down the unlatch push button, which energizes the unlatch coil, which then unlatches the coil or the relay contact, and the light goes off. So that is what our instructions of internal bits are going to do inside the PLC program. Now we have latching and unlatching as well as set and reset. They're always used in pairs and symbolized as an output symbol with a letter in the middle. They do not energize any field-connected device. Instead, they offer control of an internal bit which addressed alphanumeric, the same as the coil pair. So let me show you. Here's an example of lighting control. We have internal bit. It's indicated with a B, number 174. Notice how they're addressed identically. And there's an internal bit addressed the same as these two. So these two are like the coils that are going to control the contact of a latching relay. So these are all correlating together. We've got an internal bit latch and unlatch, and an internal bit controlled by the latch and unlatch. Control of the internal bit input is identified the same as in the relay world. All contacts controlled by a relay coil must be labeled with the same name. So R1, K2, CR1, things like that. So let's press the on button. That makes input 0 go true, which then results in the latch coil going on. Now that's going to cause B174, the internal bit that's controlled by it, to go true, which causes output 7 to go on, which causes the contactor to energize, the contact to close, and the lighting load to turn on. If I release my finger from the on, the B174 latch coil remains on. So that's the intent of this system. Either this one will be on or that one will be on, but they can't both be on. So if I want to turn off the light, I've got to go down to the off push button, push it down, and that will cause input 1 to go true, which causes B174 unlatch to go on, which causes B174 internal bit to go false, output 7 to go off, the coil to de-energize, the contact to open, and the lighting load to turn off. We release our finger from this, and what we see is that B174 unlatch remains on. So that's how a latch and unlatch system would function inside a PLC. Now PLC timers come in the same two standards that we see in the mechanical world. We have TDOD, or sometimes known as time delay on de-energization, and TDOE, time delay on energization. Now, timers in PLC programs operate in the same manner as physical timer relays, and that is that there's an initiating device, there's a timer with a coil with a delay, and then there is usually instant contacts. They change state as soon as the coil is energized, and these are not timed. And then there are timed contacts, which are controlled by the 10-second. So in this system, if I were to push down the push button, this is a 10-second on delay timer relay. That means that there will be a delay 10 seconds on the energization of the coil. So if I energize this, we have the instant contact, which will immediately go on, and then the timed contact, which will go on after 10 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now the timer contact closes and that load energizes. So the instant contacts and the timed contacts are both common in mechanical timer relay operation. In PLC timers, you will typically have the same thing. A timer is usually a box that is dragged down onto the PLC programming window, and then we get to adjust or change all of the parameters. We can change the type of timer, so an on delay versus an off delay. We can adjust the increments of time that are being measured. We then set the amount of preset time that we want to have counted. So the base time increments, the preset is how many of those are going to be counted. And then ACC, which on this particular brand, I think it's Allen Bradley, would be the accumulation of time. Now each brand will have slightly different visuals that show this, and they may not say ACC, but they will have a real-time count. Now there's going to have to be an input that's used to control when the timer is activated, in the same way that we had a push button for the mechanical timer relay. When the input goes true, there is an uninterrupted path of logic to the timer, and the timing sequence starts. So here we go, time's up. At this point, when it's finished timing, the timer may activate one or more of the following. So on some brands of equipment, you will have simply an output, and the output will go on. On others, you'll have something called a done coil. The done coil will go on, and it's used as an internal bit, as sort of an internal relay. So when that goes on, the internal bit goes true down here, that's on another line, and that controls the output. Others, again, Allen Bradley will have done and energize. The done is the timed, whereas the EN, energize, is the instant contact. So that means as soon as this goes true and allows this to start timing, this would go on, and this would go true, and output 2 would go on. So the energize coil goes on as soon as the timer has started timing. Think of this as the equivalent of an instant contact on a standard timer relay. Finally, other types of PLCs will have specifically addressed internal bits, and the addressing would be specific to the manufacturer for both the timed or the instant functions. So on some brands, they're going to just tell you, okay, for this timer, TO, for the instant contacts, you're going to label it or address it 2.15. For the timed, we're going to address it 2.16. So it's just something specific to the manufacturer that you would find in the manual. Timers can be set to automatically reset or require a separate input to reset. So this would be an automatic reset. Once it gets up to 10, then it resets. So false goes back. Sometimes you'll have to have a separate signal to reset it. So input 1 goes false, then we'll have to wait until input 2 goes true in order to reset the timer. So the time does not reset until a reset signal is received. And there we go. It is sent back down to its reset value. Counters operate very similar. You have up counters, you have down counters. Counter records each time the input goes true. The type of counter would usually be indicated as up or down. The preset, as in how many you want to have counted before activation, and finally how many are actually being counted in real time. This type of system usually requires a reset input in order to return it back down to 0. When the number of events counted is equal to the preset number, the counter will initiate an output action, and this is accomplished in the same ways identified for PLC timers. So you might have an output, you might have an internal bit done coil, and you might have addressed internal bits. I hope this gives you a basic sense as to how we deal with some of the functions of programming with internal bits, timers, counters, and set reset coils.